So in this video, I'm going to be talking about the simulation theory idea, right? And how it's less of an idea and more of a reality, but it's not this programmer in the sky thing that you've been taught, or at least you've been led to believe that it is. In reality, it's just a simulation that's created from our mental model created in our brain basically when we sleep at night, and how this is all controlled by the autonomic nervous system. And before I get into any of that medical boring stuff, I'm going to have to explain to you a few things that you'll understand, like first of all, like the curvature of time and space, understanding what Nyquist frequency is, and I'll be able to do that with some demonstrations. I'll show you how you can even reproduce these with your cell phone. So first thing we'll do is we'll get into Nyquist frequency, showing how the sample rate, right? Like imagine something is spinning, right? Like 50 revolutions a second, understanding that if I had a sensor that could only like detect 10 measurements a second, then if this is going 50 a second and this is only going 10, that this isn't a high enough sampling frequency. This would be my sampling frequency. Whereas like if you wanted to do this thing called Nyquist frequency, which is the minimum required sample rate, if this is going 50 revolutions a second, then this would need to go 100 revolutions a second, or a little bit more than 100 revolutions a second. And we'll show you how this actually accounts for a lot of the things that you don't see in real life, like these lights that we exist around, and how this is flashing on and off constantly, but you don't really see that. And you may think that, oh, it's just staying illuminated, but no, it's super slow mode. You'll see how this light here is actually flickering on and off and is actually dimming, but because we are living in this mental model, we don't actually see it. All right, so the reason why you were able to see that light flashing is because, one, this is an incandescent bulb, which means it's basically just that coil that goes in. It's not like an LED or anything that has its own electronics connected to it. But what matters here is understanding that the reason why the phone was able to record it and we don't see it is because it has a high enough sample rate. Because our sample rate isn't high enough, what would normally happen is that basically it would be on randomly and it'd be off randomly. But because we have this mental model, our autonomic nervous system, which is much faster, it's what contracts all of our arteries, controls our heart rate. Because it's so much faster, it's able to like determine that, basically this is the average of the light being on. And when I say average, it means that like for however much time it's on and how much time it's off, it's basically going to use that to make it appear brighter or darker to us. When in reality, it's the same amount of looms, but it's just looms with respect to time. So the next thing that you're going to see is you're going to see my phone in there, because this is actually used on a lot of other things. So let's imagine you had like a 10 volt battery, right? And you have this device that runs on 5 volts. Well, if you want to connect it to it, for us to not waste it, right? Like, and this is me oversimplifying a little bit, but the principle is what matters. But if you were to connect that 5 volt device, for you to not destroy this device, you'd have to cut it down to 5 volts. Well, instead of just using like a resistor or using some method where we basically burn off the excess power, which would happen in like a linear voltage regulator, what we do is we switch it on and off. It's called pulse width modulation. So it doesn't work this easily, but like let's say, for instance, like at on all the time when you flip the switch, that would basically be 10 volts. But let's say you flipped it on and you flipped it off, and like for 50% of the time it's on, 50% of the time it's off. If you did that like really fast, basically it seems like it's on to us because it's happening so fast it's outside of our conscious resolution, our conscious perception system's ability to acquisition data with respect to time. It's basically like it's basically like a minimum or maximum, I should say, refresh rate on a phone's camera or on a video, 60 hertz versus 120, and etc. So what we do here is like on our phone screen brightness, right? Like let's say you want to turn your phone screen up or down. When you turn it up and down, it'll begin that pulse width modulation cycle where it will reduce, basically cutting the power off and on so quickly. Matter of fact, that's how that fan works too, where I cut it off on so quickly that basically the average voltage gets dropped. It seems like because it's only on and off a certain amount of time, the amount of power that gets burned, it kind of levels off. And you're going to see this on my phone as I record the same light. And it's going to appear faster now in this video because the phone, like I said, is up to 240 hertz and it only requires 120 for this. But because the phone screen's faster, it has to actually display it faster, and then so it's with relationship to each other. All right, so now those same lines that you're going to see, or that you did see on my phone, the ones that are coming across as straight lines, those lines will get wider or darker with respect to how long it's off. And the reason why that is because Well, the actual camera of the phone has a higher refresh rate than the actual screen. And so it's basically doing a similar averaging with respect to like how we would average it, except because it's in pro mode, instead of it making it brighter or darker, it's literally giving you overall bar, so that way you can use the information. And so now you'll watch what happens when like you move with respect to that curvature, and that curvature which is updating with respect to time and movement. And the thing is people say like, you're always moving through time, but you're never moving. They say that basically no matter what, you can stand still in space, but you can't stand still in time. That's not true. You really can't stand still in space, because in space, even if you're not breathing, there's diffusion from your skin, whether or not it be heat, whether or not it be moisture. There's your actual heart rate. There's all these little mechanical movements. The Earth moving around at about 1,000 or so miles an hour, shooting through the atmosphere, the galaxy at like some ridiculous speeds, following the sun around. So we're always moving in space. You're never not moving in space, and because you're moving in space and time, you're going to get a curvature. So right now you're seeing a little bit of both, right? You're seeing what happens with the pulse width modulation that I described on the LED. Basically, that little LED light at the bottom of the phone, because it's not at full brightness, you're seeing it shut on and off. And on the screen, it's representing that as an average of on-off black line thicknesses. It's the same thing that's happening on the actual display itself. And you can see this, that basically, if I was to turn the screen brightness up, those black lines would get thinner. If I turned it down, those black lines would get thicker. But really what's happening here is that the phone screen is on and off really quickly. The same way the light was in the home. The only difference is because the screen's resolution doesn't have the ability to match that on-off cycle. What you're getting now instead is because the camera lens is capable of detecting this on-off, but the screen isn't capable of displaying it, it's giving you an average based on the thickness. So now as I kind of like rotate the phone back and forth, you'll see the lines look as if they're coming from a different location. See, as I turn the light on and up, so that's full brightness. You see it going down, the black lines get thicker, and it's just like a little less there. But we're gonna see if we can't get you some nice curvature now. And curvature is basically gonna be what the screen looks like with respect to the motion of those lines, and also movement with respect to the phone. All right, starting to see a little bit of curvature there, obviously. What you're going to want to do to be able to reproduce this basically is you have to have a phone with a camera manual mode. And with that manual mode, what you do is you turn the shutter speed up really high. Now, when you turn the shutter speed up high, what happens is it makes everything in the surrounding very dark. So you have to turn up your ISO rating as high as you can, and you want to make the rest of the room dark, which is why it appears in the way it does. It's just because my ISO is high and my shutter speed is very high. All right, so please like, share, and subscribe so that way you can see the part 2, where I'm going to try and get into the medical aspects and how this all connects to our physical reality. So there's one last thing that I thought I should add to the end of this video, and it's basically just going to give a little demonstration as to where the idea of higher dimensions come from and how dimensions are formed from the symmetries of other lower dimensions. All right, so this is just the first little example to show you where the idea of dimensions come from. So what you need to understand is that these little dots are all going to count as zero-dimensional points, right? So then how would you get yourself the symmetry between two zero dimensions? You just draw yourself a line, and that becomes one dimension. So one dimension, right, is just the symmetry between two zero dimensions. Similarly, if you want to go to a two-dimensional object, the two-dimensional object is made up of symmetries, right, between two one-dimensional objects. So now we draw this, and we got ourselves a box, right? Kind of crappy. And you do the same thing here, right? So now you have yourself two two-dimensional planes, like such. And what you do is you draw the symmetry between these two, right, boxes. And then now what you have is a three-dimensional plane. And all you did was just symmetrize these two dimensions to get three-dimensional object. And then you keep building like that. And so then the next dimension would be the symmetry between two three dimensions, which that would be more difficult, obviously, because it becomes more difficult just to represent it here on a two-dimensional plane, a three-dimensional object. But you kind of get the point as to where this comes from now.